are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about the application of nanomaterials that for mass transfer operations. So, here already in our previous class we already have discussed the various type of nanomaterials, metal based nanomaterial, metal oxide based nanomaterials, and that can be applied for that mass transfer operations. And today we will discuss nanofluids for that mass transfer operations. So, here synthesis of nanofluids, that is particularly consist of nanomaterials or nanoparticles and base fluid or liquids. So, how that nanofluids can be synthesized, what are the various methods are available. So, based on that we will discuss, and then CO2 adsorptions by nanofluids, that we will discuss, and then MOF metal organic framework, that is mesoporous materials. So, that will be for CO2 adsorption study, and how that MOF can be composite with the nanomaterials or nanoparticles. So, that will be discussed, and then MOF composites will be used for that CO2 adsorptions, and then so we will discuss about convective mass transfer for nanofluids, and then so how the flux and mass transfer coefficient can be calculated by experimental this mass CO2 absorptions or concentrations that would be changed. Flux this means from gas to fluids or nanofluids, how the CO2 concentrations means changes, rate of mass transfer that will be calculated, means also we will discuss about. So, considering base fluids, what would be the mass transfer coefficients, and if we add some nanomaterials in that base fluids, means nanofluid preparation. So, then how that would affect for overall flux and mass transfer coefficient, that we will discuss. So, here application nanofluids, that is actually it is synthesized by considering nanoparticles and one base fluids, that is that media we have to use to prepare it. So, first in known quantity of nanomaterials, that would be nanoparticles, metals, metal oxides, that would be put in the fluids mediums, and then that would be mixed, and then ultrasonications or vibrations. So, using that would be mixed up properly. So, then at the end we will get nanofluids. So, here we will discuss about the preparing of the nanofluids using nanoparticles in CO2 absorption solutions, how that improve the stability for that enhance of CO2 absorptions and desorptions or mass transfer process. So, that we will discuss. Particularly the absorptions or desorptions process, that depends on that what type of fluids that we are using and what type of nanomaterials or nanoparticles that we are using. So, depending upon the use of or choosing of the nanomaterials or nanoparticles and the base fluids. So, depends on that nanofluids, the separations means CO2 from any flue gas. Suppose it has a particular concentrations, we can separate them out by considering mass transfer gas liquid contact process. So, then we can reduce the disposed CO2 from that flue gas. So, by that way we can increase the separate out the CO2 by mass transfer operation by using nano fluids. Okay. So, here usually nanofluids, it has been observed that using conventional fluids, instead of that if we use nanofluids, so the performance observes it is better than conventional fluids. Nanofluid is perform better for CO2 absorptions. So, and in relevant to this, so number of research publications, that is gradually increase year to years, if we notice. So, gradually increase on this, and this nanofluids has lot of applications: medicals, wastewater, water purifications, solar collector, heat exchanger, vehicles, batteries, many places. So, that are used. So, here the nanofluids that actually defines, it is consist of nanoparticles. The nanomaterials may be 1 to 100 nanometers within that range, and a base fluids that you have to use. So, here if you use base fluids as a water, so deionized waters we can use. So, and then amine based nanofluids also we can use. So, here methyl diethanol amines, monoethanol amine or methyl diethanol amines, diethanol amines, piperazine, DAB, theta or AMP, or mixtures maybe MEA and MDEA mixtures we can use as a fluids, and that can be used for the separations of mass transfer operations or CO2 separations. Okay. So, here's different type of nanomaterials we already have discussed, that we have synthesized by considering a particular method. So, the nanomaterials may be metal oxide based, non-metallic oxides, graphene oxides, or carbon based nanomaterials also, carbon nanotubes, multiple carbon nanotubes, and this is metal oxides based, or some magnetic nanomaterials, that is ferric oxides that can be used as a nanoparticles that can be mixed with waters or amine based fluids. So, by that way we can prepare a nanofluids, and that can be used for the CO2 absorptions in that particular fluid. By that way we can separate them out. So, here it has been observed that alumina, silica, these are the nanomaterials we can use for that absorptions of CO2. It performs better with very low concentrations we have to use, and sometimes if you want to go for CNT or ferrous oxides in that nanofluids. So, here low concentrations of, means in case of the alumina silica, so we have to use high concentrations of nanomaterials in that particular fluids, and if we use CNT or ferrous type of nanomaterials to prepare the nanofluids, so in that case low concentrations of that nanomaterials we have to use, so that would perform better. And even CNT also we can use for DEA solutions. Okay, so here a table is given by considering different type of nanomaterials based fluids and enhancement factors for mass transfer operations of CO2 absorption capacity. So, here you can see alumina if we use 0.058% and base plates DA. So, then enhancements of CO2 absorption that has been increased into 33%. Similarly, if we use magnetic nanomaterials Fe3O4 0.39 weight percent MDA in the base plates, and then it has been observed that it has been increased the CO2 absorption capacity 92.8 percentage. Similarly, for silica and others metal oxides and different base plates also. So, depending upon base plates and nanomaterials, the enhancement percentage is also different. Okay, so now we will go for preparations of nano fluids. So, there are various methods. So, one step methods are there. So, in this particular method, this method is very simple method. So, in this methods we can discuss there. So, then next is two steps methods is also. So, this is for bulk scale productions or industrial scale productions it can be used, and here in one step methods. So, basic difference is that we can take nanoparticles in that base solutions, and then in one times we can put, and then we can mix them up with the help of stirrers or some other way. So, then we can get homogeneous mixtures of nanofluids, and in two steps methods, in addition to that, in the second steps we can use some surfactants or sonications. These are the additionals to improve the stability of the nanomaterials in that fluid. So, that we can do. So, by changing with the nanomaterials, so surfactants we can use, at the same time sonications that also we can do performs to get a better stability of the nanomaterials. Also some other methods are also available, that is the phase transfer method. So, in that case suppose a gold nanoparticle, so we have prepared in aqueous solutions, then that would be transferred to any organic solvent or hexanes through magnesium chloride and sodium oleate. So, that is the phase transfer, means aqueous to non-aqueous phase if you want to transfer. So, then phase transfer, this is called phase transfer method, or post treatment method is also there. See, here a high pressure homogenizer we can use in addition to the sonications, surfactants use. Homogenizer that can use, by that way you can maintain extremely high pressures. So, that would help to improve the dispersions of the nanomaterials or nanoparticles in that base fluid. So, therefore, we can get a more stable solutions. So, that solutions may stable for a longer period of time. So, for that particular application that would be good. And in one step methods here we are going to discuss. So, in one step methods I said base plates you have to take and nanoparticles you have to take. So, both you have to mix them up in this, and then we have to mixing them up, then we can get nanoplates. So, in here key steps means different type of procedures is there. So, key techniques, that is vacuum evaporations onto a running oil substrate, that is methods, direct evaporations conditions methods, or submerged arcs nanoparticle synthesis method is there. So, in one step methods, in this particular methods advantages means reduce agglomerations and improve the stability of that nanomaterials by using stirrings or dispersing these nanomaterials in that fluids. So, in this case This is the advantage, means in one step method. So, and here's this disadvantage is high production cost in one step method. So, that is small scale preparations we can use, but for large scales and industrial productions you have to go for some others better methods. So, that is say means two steps methods, that much more better. So, this usually used for industrial scale productions of nanofluids. So, in this case I said we have to take one base fluids, so that may be waters or any other solvents, and then surfactant we have to add, and that surfactant may be SDS, PVP, PEG, CTAPs, SB, SDBS, oleic acid, acetic acid. So, this type of means cationic or anionic surfactants or neutral surfactants we can use depending upon that preparation. So, in these methods large scale productions I said, so it is suitable for large scale productions of the nanofluids, and here it works for different type of metal oxides if you use as a nanomaterial. So, that easily we can prepare by using two steps methods, and easily we can adjust pH and surfactant concentrations, and also independent, it allows independent controls over nanoparticle synthesis and fluid selection. So, which particular fluids selection we have to use for this particular nanofluid preparations. So, independently we can select the nanoparticles as well as fluids. Okay, so here some disadvantages there. So, here if you use metal based nanoparticles, that is not suitable for these two steps methods. Here maybe oxidations or agglomerations possibility is there. So, that is since we are using some metals based, metal nanoparticles is very small size, so that easily may get oxidized. So, therefore, this is not suitable. So, if we use metal oxides, so then it is good in two steps methods. Okay. So, in two step methods we have to use a base fluids here, and then nanoparticles we have to put it here, and then we have to use some surfactants, and then we have to do ultrasonications, and then we can get nano fluids, that is in first steps I said nanoparticles and base fluids both will be mixed in the first stage, and then you have to use surfactants, then we have to do the stirrings in the second steps. After that ultrasonications we can do, and then we can get nanofluids. So, now the stability measurement of the nanofluids. So, by using or choosing the nano base fluids and nanomaterials, so we can prepare say nanofluids by considering one step methods or two step methods, and then we have to see the stability of the nanomaterial. So, means when nanomaterial is very small particles that would be distributed in that particular base fluids. So, if proper mixing is not there, and stability is very crucial for that get that particular properties for mass transfer operations. So, the stability of the nanoparticles we can measure by using DLS, UV spectrometry, microscope method, zeta potential and turbidimetry methods. Many methods are there. So, using these methods, so we can see the concentrations of the nanoparticles within that base fluids and how long that is stable, means with increasing time. So, it has been observed that the stability of the nanoparticle gradually decreased as a result. So, the fluid means would not works properly when we apply for a specific applications. So, DLS methods already have discussed. So, in this particular way means dynamic light scattering. So, where nanoparticles that would move inside of the fluids in Brownian motion. So, with that would be interact with the lasers, and then we can measure the hydrodynamic boundary layers, hydrodynamic diameters of that nanomaterials or nanoparticles that is dispersed in that particular waste fluids. In visualizations methods also or microscopic method is there. In this methods we can detect particles if it is greater than 0.2 micrometers and not suitable for smaller nanoparticles. If particles is very small diameter, so we cannot measure properly. And zeta potentials also we have discussed. So, what is called zeta potentials, and if we have a prepared say stable base nanofluids, so then the zeta potentials value either plus or minus. So, that would be good if it is greater than 25 plus minus electron millivolts. So, then we can say it is a stable fluids, and if it is 40 to 60 millivolts, so then it is also much more better, or it is ideal, so we can say. So, higher potentials, zeta potentials, stronger repulsions, and that means the nanoparticle does not interact with each others and give a stable solutions. Also turbidimetry methods, that is also that nanofluids we have prepared that we can measure the stability of the materials. So, here we can observe the mobility of the nanoparticles that is suspended in that base plates or nanofluids. So, here high turbidity of that nanofluids that we have prepared, it means more particles suspended in that nanoparticles. So, higher nanofluid stability. Okay, so high turbidity means higher stability of that nanomaterials, and that is stable solutions. So, here some each methods having some principles, advantage, disadvantage and applicability that has been summarized. So, already we have discussed and summarized here. So, once UV is spectrometer methods we can use for characterize the stability of that nanofluid. So, here some limitations is there in this method. So, we cannot use highly concentrated solutions and dark solutions we cannot use. So, here depending upon the nanomaterials and base plates. So, particular wavelengths UV's wavelengths we have to use to get that means measurement of that stability of that particular nanofluids. Here once the stability of that nanofluids that we have prepared by considering CNT or ethylene glycols, that is the base fluids. So, here no surfactant was used, here zeta potential greater than 45. So, it means it is highly stable. So, stability I said zeta potentials is higher, the stability of the nanofluid will be gradually increase. So, here zeta potential 40 to 45 good stability, and when it is 60 then it is excellent stability. So, here different nanofluids. So, it may be stable for 2 months or maybe 3 months. So, depending upon the nanomaterials we have used and base fluids used, surfactants used, and the property we can measure by considering zeta potentials, and then we can say that whether how long that fluids that we have prepared, that fluid will be stable. So, now in applications point of view, so CO2 absorptions in nanofluids. So, enhancement mechanisms means how nanomaterials when it is dispersed in nanofluids, nanomaterials. So, we have used to prepare a nanofluids. So, in CO2 absorptions, how that enhance or increase the enhancements or increasing the CO2 absorptions performance in mass transfer operations. So, here in nanomaterials, so when CO2 that is remain in the gas phase and nanofluids that is with the base plates nanomaterials that is in liquid phase. So, both the phases gas and liquid come in contact, and then high concentrations gas, that is CO2 presence in gas stream. So, that would be come in contact with the liquid or the base fluid. So, there mass transfer due to the concentrations difference or driving force, mass transfer operations will take place from gas to the liquid, CO2 will move. So, here the gas that would be in the form of bubbles, and in that base fluid, so nanofluids, so there's nanoparticles dispersed in the form of particles. So, in that nanoparticles actually helps to collapse, actually that's bubbles nanoparticles, CO2 nanoparticles leads to the bubble collapse. So, as a result increasing the mass transfer from gas to the base fluids, the CO2 will transfer more. Okay, so, increasing the gas and nanoparticle contact area that would enhance actually CO2 absorptions when we are using nanoparticles and prepares a base fluids, and that base fluids in the nanofluids are using for CO2 absorptions. Also, if we use some nanoparticles, that is the solid particles nanomaterials, so that actually disrupt the boundary layers. So, here you can see this is the boundary layer in between liquids and gas. So, if we put some nanomaterials, so then that boundary layer thickness that will be decreased due to the presence of nanomaterials. As a result, mass transfer resistance will decrease or reduce, and then boundary layer thickness also will reduce, and therefore increasing the mass transfer coefficient or rate of mass flux, that rate of mass transfer mass flux will increase. Also, grazing effect is also there, means nanoparticles migrate along the gas liquid interface and temporarily absorbing CO2 before returning to the bulk liquid to dissolve it. So, grazing effect is also important. So, here means nanoparticles that helps in gas absorptions. Okay. So, here it has been observed that CNT when we are using that having high surface area, so that absorbs more CO2 than sulfur dioxide. So, in particular experiment it has been observed that CNTs means show better performance when CO2 is used for as a nanomaterials to prepare a base fluid nanofluids, then CO2 absorption performance is much more better than sulfur dioxide absorption. So, here zinc oxide nanoparticles in water. So, zinc oxide nanoparticles nanofluids we have prepared. So, that can be used for CO2 adsorption. So, here the CO2 interact with the nanoparticles that is present in the nanofluids. It forms monodentates, bidentates or tridentate type of structures, and that adsorbs or assist means absorbs that absorption mode of CO2 in the oxide nanosurface. So, different mode of bidentate, monodentate or tridentate way that CO2 get adsorbed over the zinc oxide nanoparticles that is present in waters. Okay. So, similarly amino functionalized silica. So, we can take silica SiO2 that is nanoparticles, and there if we functionalized with amino groups, so then it would increase the CO2 adsorptions by formations of different type of carbonate bicarbonate species with that and no functional groups. So, that way it would enhance the CO2 adsorptions. Similarly, if we use MgO water nanofluids, so their CO2 adsorptions also increase. So, by formations of bidentate carbonate type of species. Okay, so depending upon the nanomaterials, whether it is monodentate, bidentate, tridentate, means CO2 structure or CO2 adsorb structure, or here formations would be theirs, or bicarbonate species or maybe bidentate carbonate species formations would be depending upon the nanomaterials we are using. Depending on that, different type of CO2 will get adsorbed, different way CO2 would get adsorbed, and adsorptions enhancements also would vary. Means here you can see all are the base fluids and different type of nanomaterials or nanoparticles that are used, different concentrations it was used, and then absorptions enhancements also, percentage enhancements also are different, so that would vary. Okay, so and all this was done at 25 degrees centigrade, means when we go for CO2 adsorptions, so you have to use very low temperatures for adsorptions, and different type of reactors we can use, bubble column reactors, single bulb or high pressure batch reactors, packed columns we can use, tray columns also we can use, depending upon the applications we can different type of absorptions columns we can used. Okay. So, and now these CO2 adsorptions by nanofluids, that depends on key parameters, means we have nanofluids, there's nanomaterials is present, different type of nanomaterials, that may be metal oxides or maybe carbon based nanomaterials at very low concentrations we can disperse in that particular fluids to prepare nanofluids. And then how that CO2 means experiments if you want to conduct in any particular reactor, so then observer, so then CO2 inlet concentrations, that is very important. So, that CO2 present in the flue gas or in any gas, their CO2 we have to separate out, that concentrations very crucial. So, if we use very low concentration or high concentration, based on that the adsorptions of the CO2 in that fluids or nanoparticles, so that would vary. So, if we increasing the CO2 volume fractions in that particular flue gas, so then that would enhance the CO2 absorptions. Gas flow rates, gas liquid flow rates is also important. So, that also change the mass transfers for gas CO2 gas adsorptions to the base fluids, that also will affect. Even temperature I said, normally we use for adsorptions low temperatures. So, 25 degrees centigrade is very suitable. So, if we increase the temperatures, adsorptions of CO2 in that nanofluids will decrease. So, pressures, increasing pressures, that would increase the solubility of CO2, even nanoparticle size. So, that thermal conductivity, for example, in nanofluids, that increases as the nanoparticle size increases from 11 to 16, 11 to 63 nanometers. So, let us say this alumina having 11 nanometers particle size or 63 nanometers particle size. So, increase means thermal conductivity of that fluids will increase. However, that means using different diameters or size of the nanoparticle, the fluid property changes thermal conductivity. However, the CO2 adsorptions may affect or may not affect. So, that does not increase significantly in case of alumina based nanofluids that was observed. So, not significantly change in the mass transfer operation. So, nanofluid type also depending upon different type of nanomaterials. So, that also absorption performance also will change. Even nanoparticle concentrations that also will affect. So, if we use low concentrations of nanomaterials or high concentration of nanomaterials, that also will affect the overall performance of adsorption. So, here for CO2 adsorption desorption experiment or mass transfer operations are using nanofluids. So, here is experimental setups is there. So, how that fluids will perform for CO2 adsorption desorption. So, here CO2 gas cylinder was taken. So, here is the absorber. So, here's base fluids, that is CO2 lens adsorbents that was passed through here, and gas is passing through here, it would be mixed. So, then gas means CO2 and nanofluids come in contact and mass transfer operations will take place here, means CO2 gas will be absorbed in the nanofluids, and after that, so CO2 rich adsorbents that will be passed to the regeneration. So, by that way, from whatever the amount of the CO2 get adsorbed in that base nanofluids, that again will be heated up or increasing temperatures. So, we can get that CO2 gas. By that way, from any gas mixtures where CO2 is present, so we can separate them out by using absorber and regenerator. So, by using nanofluids. So, enhancement mechanism for CO2 desorption. So, once here CO2 absorptions will be there, here CO2 desorptions will be there. So, CO2 desorptions that depends on the also activation energy, means nanoparticles enhances the collisions and disturbance with activation energy, leading to increase the CO2 desorptions. So, if you means create some turbulence in during desorptions, so then that would help to CO2 desorptions. So, also thermal effects. So, means if we heated up that, suppose nanofluids here, nanofluids we have taken nanofluids here. So, if we increase the temperature, so then the desorptions will increase. So, that is called thermal effect. So, enhance the heat transfer. So, we can improve the heat transfer and we can increase the desorptions. Okay. So, here desorptions we can increase. So, if we want to get more adsorbed CO2, so then we have to down the temperature. If you want to get desorptions, more CO2 desorptions from that nanofluid, so then we have to increase the temperatures. Okay, sure. And so also bubble formations or enhanced weightability, that also affect the desorptions of CO2 from that nanofluids. So, here I said that thermal effect, that is very crucial for desorptions of CO2 from that nanoparticle from the nanofluids. So, here, so how that nanoparticles, when we are using in a base fluid to prepare a nanofluids, and that nanofluids are using for CO2 adsorption desorption. So, here nanofluids actually, here CO2 bubbles and this is hot surface. You can see here, if we place nanoparticles, so nanoparticles actually enhance the heat transfer. So, from here heat would be transferred into the bubbles, and then so that would helps to desorptions of CO2. So, here the temperature rise, so that has also critical value. So, we cannot increase any temperature. So, once it reach to a critical value, then the desorptions, the solutions from bubbles and nanoparticle enhance the desorptions. So, here these are the nanoparticles. So, if we reach a particular temperature, so then nanoparticles assist to dissolve that CO2 that was adsorbed in that nanofluids. Okay. So, we have discussed about the role of nanoparticles for CO2 adsorption desorptions or mass transfer operations for using nanomaterials in the base fluid to prepare a nanofluid. So, now nanoparticles that would be mixed up with the metal organic frameworks to prepare nanoparticles MF composites. So, that also can help for CO2 adsorptions or mass transfer operations. So, that will increase the performance. So, MOF is having a good surface area. So, this is the nano composite MOF preparations. Here usually MOF we prepare by using some metal salt and organic ligands. So, by condensation methods or precipitations by stirrings, we can prepare this nano metal organic frameworks. So, nanoporous materials that already have discussed in our previous class. Or so, after that, different type of MOFs depending upon the usings of metals, which particular metal salts we are using. So, depending upon that, and also these linkers, organic linkers. So, depends upon the different type of MOFs that we can prepare. So, and once MOF we have, so then with that different type of nanomaterials we can incorporate into that MOFs during synthesis or after synthesis. We can means once we have a pure MOF materials, there's a particular nanomaterials we can impregnate, or directly when MOF would be prepared, then also a particular quantity of nanomaterials we can add with that synthesis process. So by that we can incorporate different type of metal oxides nanomaterials in that nanoparticles into the MOF. So here's graphene oxides. Here the synthesis of graphene oxides MOFs that I am showing, graphene oxides, and this is metal salts and organic ligand that would be used for MOF preparations, and both graphene oxides and these salts and organic ligands both will be taken in a beakers, and then it would be followed the hydrothermal treatments that already have discussed. So by that way you can prepare geographene oxides impregnated MOF that we can prepare. So here step by step methods is given. So here's this is the link organic linker we can use, and here copper nitrate that was used as a metal precursors, and amount of graphene oxides we can change different amounts depending upon the materials we want to prepare. So here copper MOF with that CO2 was impregnated. CO2 is the nanomaterials. So copper salts and trimesic acid was taken, and then in solvents and by hydrothermal methods we can prepare the MOF, copper MOFs, and then we are putting ceria here, CO2, and then washed with DMFs, and means this ceria would be mixed up with that copper MOF, and then by washing drying, so we can get copper MOF impregnate with cerium CO2 ceria nano particles. So it is get nano composite we can say. So it has been observed that when graphene oxides that was impregnated with MOF, so how that is enhanced means here different quantity of the graphene oxide 2%, 5%, 8%, 10% was impregnated with MOF 505 materials. So here graphene oxides having very low surface area, MOF having extremely good surface area. When 2% of graphene oxide impregnated with the MOF 505, then surface area you can see enhanced. So in 5% we are adding graphene oxide, then surface area means 1100 to 1279. So surface area increase, good amount of surface area we are getting. So therefore these enhancements of surface area in that graphene oxide composite that would of course help in CO2 uptake when CO2 adsorptions experiment we will conduct. Okay, so here it has been observed that you can see the CO2 uptake, so 2.87, so that was observed. So in that particulars means of graphene oxides was used. So in parents compounds, here is the parents means only MOF was used, MOF 505. So in that case it was 2.87 millimole per gram CO2 uptakes, and whence graphene oxides was incorporated with MOF 505. So then CO2 uptakes is this. So it is enhanced means additions of graphene oxide, and make that if we are able to make that graphene oxide MOF 505 composite, so then CO2 uptakes 2.87 millivol to 3.94 millipole per gram CO2 uptakes has enhanced. So similarly other different nanomaterials also incorporate in the MOF, and then we can prepare that composite MOF, so that would enhance for CO2 adsorptions and selectivity. Okay. Similarly here also different type of MOF and CO2 adsorptions that has been shown here. Selectives means depending upon the gas mixtures also, so it selectively may get adsorbed if there is some other gaseous molecules, let us say methane is present within natural gas. If a certain percentage of CO2 is present, then the fuel value of the natural gas would decrease. So if we are able to separate that CO2 percentage from that natural gas, then the fuel value will increase, and for that this type of composite materials we can use to absorb that CO2 that is present in the natural gas. Okay. So here it has been shown that comparison of CO2 uptake with the pressures, and by considering different type of MOF. So MOP 7177 that has been observed, CO2 uptake is higher. Okay, so this is the summary for synthesis of the nanofluids that we have studied or we have discussed. Then CO2 adsorption by nanofluids, MOP CO2 adsorptions and MOP composite we have synthesis, and then MOP composite was used for CO2 adsorption that we have discussed. Okay. So apart from that, various type of mass transfer equipments are available, convective mass transfers. So that would increase or enhance by using nanofluids. So here different type of systems you can see, means convective mass transfer by using nanofluids. So that experiment we can do by agitated absorptions reactors, 3-phase airlift reactors, bubble type absorption system, falling film absorption systems, tray column absorption systems, gas liquid hollow fiber membrane systems, or direct measurements of mass transfer coefficient and nanofluids. So and liquid liquid extraction systems, these are the various type of reactors or systems, means two phase contact equipment. So means gas and liquid contact operations reactors or systems, you can absorption columns you can say. So that are available. So there's two different phase, means nanofluids and the gas where CO2 rich gas is present. So that we can pass and they will come in contacts, and then mass transfer operations will take place from gas to liquid. CO2 will transfer due to the here one agitated gas absorption reactors is showing. So here we can use nanofluids, we can stirring here, and then oxygens and different concentrations with the help of nitrogen we can pass here in the forms of bubbles or spurgers is here. So it would be mixed up, and then the concentrations of CO2 O2 we can increase in that particular base fluids. So this is experiment. So different type of nanomaterials we can use. So here these are the things I am not discussing more details. So almost basics or key principles of different type of absorption systems or columns is same. So we have to use a specific nanomaterials to prepare say nanofluids, and then that we have to use either in the flow conditions or stagnant conditions, and then that gas having CO2 rich gas that would be passed through that. So then that mass transfer operations will take place and CO2 would get adsorbed in that base plate. So by that way we can and separate out CO2. So here in the one experiment is there here in lab scale. So here CO2 gas cylinder is there that would pass through this mass flow controller. Here we can use nanofluids, nanoparticles loaded, metal oxide nanoparticle loaded nanoparticles or nanofluids, you can place it here, and CO2 rich gas would be passed here in the form of bubble formations is there. So gas would be coming out, and then that nanofluids we have present that would be adsorb that CO2 gas, and then that CO2 gas means that fluids we can take and titrate, and the amount of quantity of CO2 gets adsorbed. So that we can find out. So by considering base solutions, so how much quantity of base is used, so that would gives the quantity of that CO2 gets adsorbed. Okay. So here's concentration of the CO2 we can find out. When initially it was 0, and then so when CO2 gas is passed through that, so then amount of CO2 get adsorbed in that base plates, we can find out the concentration by considering the M is the molarity of that HCl that was used. This is the volume of that adsorbents used in that columns, and V1 and V2 that is the changes of the volume to neutralize that CO2 that is adsorbs and bicarbonate formations is there. So this is, and then once we know the CO2 concentrations, then we can find out the average flux of CO2, rate of mass transfer from gas to liquids that we can find out. So concentrations we can put, V you have to put, and total number of bubbles passes through these nanofluids we know, and individual bubbles radius if you are know, then bubbles surface area, total surface area, and T is the time conductance. So then flux we can calculate, and then once we know that average flux and bulk concentrations and interface concentrations of that CO2, and then mass transfer coefficient also we can find out. So, here you can see for particular CO2 gas absorptions, here base fluid was water, here mass transfer coefficients KL you can see 1.030 meter per second. So, here when silicon dioxide SiO2 nanofluid was used and prepared water silicon dioxide nanofluids, here you can see that enhancements of mass transfer coefficient 1 to 1.935. So, that is the actually roles of nanoparticles and prepare the nanofluids that enhance the mass transfer coefficients, and as a result enhance the mass transfer rate of mass transfers. So, when we are using instead of base fluids nanofluids we are using. So, even we can measure the diffusivity. So, if we know the flux and then using these Frost-Link correlations, if you know Reynolds number, Smith number, so then heat mass transfer coefficients we can find out, and by using these equations diffusivity we can find out. The diffusivity actually express a capital D, that is meter square per second. So, here you can see for CO2 if we use deionized water, so that diffusivity was 2.12 into 10 to the minus 9 meter square per second. So, when silica used as a nanomaterials in waters to prepare silica water nanofluids, so then diffusivity also enhanced. So, 2 to 5.38 that enhancements we can observe. So, depending upon other nanomaterials also, the diffusivity of that particular component, that is CO2 in that fluids will enhance, means nanoparticles enhance that diffusivity mass transfer coefficients for a specific operations for the separations of any component, that may be CO2 separation or oxygen absorptions, ammonia separations from any gas. So, that base fluids and nanomaterials has play a significant role to enhance the mass transfer operation. So, thank you. So, today is up to this.